The PDF I sent you gives you an idea of the kind of things that I expect in a lab report. Do you have any questions as to expectations from the lab report?
None for me.
Okay. So as I mentioned last week, this part doesn't have a theory section. So usually, in the lab we have a theory section. We have to derive equations. And by the way, the lab sample lab I sent you doesn't really have a theory section, but I couldn't find one. So you don't have to rewrite any of this stuff. So basically, you have to fill in blanks. For those of you at 205, you kind of, it's the same procedure as you had in 205. You fill in the blanks. Okay, you don't have to write anything new. You will have enough to keep you busy on these lab reports. Answer the questions that you see. Fill in the tables. Notice where it says table, title. That probably means somebody wants you to write a title for that table. Okay. Fill in the blanks as you go. And here's the data tables. I had 3 labs last week, so I have several graphs here. Remember that your graphs have to have a figure caption. I gotta use spell checker. And make sure that the results of your curve fit are in your graph, because that's something I grade on. I need to see this because I need to understand that you know what you're doing. Okay. Whatever the information that I need really is because of the fact that I need to see that you know what you're doing. If I don't see this information, then I'm going to take off a point. Okay. And graphical analysis automatically shows you this information. You just got to make graphical analysis to show it. If you're using SciDavis, you're going to have to do what I did last week and add that text box. For part 2, again, for table 2, just fill in the blanks as needed. Watch the units. Make sure your units make sense. And then for the last part also, Tyler's making a video, I think, on his lab. So remember, don't do table 4 because the ammeters that we were given don't have a microamp scale, so it'd be impossible for you to do table 4. Just do table 3 of part 4. Okay. And I imagine this might be the hardest part of the lab for you because you have to have a potentiometer, and you'll have it'll be a little bit different. If you can build this circuit, you're going to have no problem the rest of the semester. And then at the end, it asks for these conclusions, and I'm not looking for a formal conclusion. What are your conclusions from that section? What did you observe in those sections? That's really all I'm looking for. What did you learn? Normally, I'm sorry? Is there a question? Normally when I look for a conclusion in a lab report, I ask you to say what you did, summarize your results, do the results agree with theory, etc. This lab is a little bit different. I just want to see what you learned and how you interpret the graphs. Okay? So this is not really a formal conclusion. This lab is a little bit different. The lab I sent you, the sample, actually the student wrote a formal conclusion. The one thing about this lab too is you're not really doing air propagation yet. Okay, what you learned in physics 205, if you had physics 205 here, I know you did a lot of air propagation. So the next lab, you will be doing that again. So this lab report is going to be written. There's no videos for it. You will not create a video. You're just going to write a formal lab report. of your results. Are we clear on that? Are there any concerns or anything regarding this to report? And this one, if it's turned in late, then I will start docking points because it's not a, I mean, it's a written report, and most of you folks have done this before based on last semester. So with the videos, because it was new, some people turned them in a little bit late, and I was okay with it because I know there was issues with uploading the videos. And by the way, for video lab reports, it really helps if you either, some of you folks did it in Canvas, which was great, but I haven't really spent time with that. I apologize. But some of you folks put them on YouTube. That's that's much easier for me to view if you just give me the link to YouTube, or if you do it in Canvas. Okay, but if you do the video and upload it to YouTube, it's just give me the link and I'll watch it, and you can make the video unlisted. So only the people who have the link can watch it. So now, of course, have you had a chance to actually start taking data on the lab? Because this will be due soon. No? Okay. And the reason why I asked you right now is because I'm not going to see you until Friday. So, okay, so if you do come up with questions, can you please post them on the discussion board for this lab? Because I'm sure you're not going to be, if you have a question, there will be somebody else in the class who has a similar question. So I'm going to then talk about the diode briefly. All right. And there's not a lot for me to say, at least in this class, on the regarding the diode. So you're wiring a circuit that looks kind of like this. By the way, I did email you the color code for lab. I didn't realize that your kits didn't come with the color code, so I emailed it to you. So we left off talking about this diode. It's a semiconductor device, and when it turns on, the voltage drop across it is, and it depends on the diode, between 0.2 and 0.8 volts. Typically it's 0.6 volts. If you plot I versus V, graph looks like this. And actually we'll cross it a little bit, but maybe I shouldn't draw that line. And I is given by this equation. Hold on a second. I need to look up a couple of constants. Just 1 second. Where V sub t, actually let me write it this way. V sub t ends up being K is called a Boltzmann constant, which is hard to remember. And the T is in temperature in Kelvin. So most likely this number is about 300 Kelvin. If you don't have a thermometer, just assume 300 Kelvin. This comes out, V sub t is approximately equal to 0.026 volts. You can calculate it yourself. N is a number between 1 and 2. And that depends on how the diode is constructed. If it's a single diode or it's part of an integrated circuit. So what you're going to do is collect data. I is a function of V. And you actually, before you collect the data, you have to play with the potentiometer to see how these two vary with each other. Because you have to be able to collect a lot of data points here. Because if you don't, you're not going to be able to fit to this graph. Okay. And again, all this thing does is limit, it turns on. Once it turns on, the voltage drop is between 0.2 and 0.8 volts. Typically it's 0.6 volts. And the voltage drop is that value across it. If you hook it up backwards, you will get a small current going through it. It's in microamps. I was going to have you do that, but because our multimeters don't have a microamp scale, we can't do that part. If you put too much current in the reverse direction, this thing breaks down and does that. So you don't want to put too much current, you don't want to put a big voltage drop in the opposite direction. Otherwise, you'll destroy the diode. Now there's a special diode which is designed for that. It's called a Zener diode, but we're not going to be using that kind of thing. And we're not going to be spending a lot of time on diodes. And they have various applications in circuits. For example, if I drew the following circuit, let's see. With two diodes. So I have two diodes and I have that circuit. That's actually an important circuit. Let's say if I put 5 volts here, this voltage will be, and I can put in anything there. Let's say I put 0 volts here. The voltage here will be around a little bit less than 5 volts. The voltage drop across here, from here to here, will be around some number a little bit less than 5 volts. Whether I make this one 5 or this one 5, or both of them 5, the voltage drop here will be 5 volts. If I make both of these 0 volts, then the voltage drop across here will be 0 volts. And this is part of digital logic. This is a simple version of a digital circuit. This is called an OR gate. This is an application of the diode. Okay, your computers are based on digital logic. All right, so this is an OR gate, and of course you can make something called an AND gate, etc. So there's application of this. Okay, there's a lot of applications of diodes to in circuits, and we won't get to this here, but you will if you take Engineering 17.
So,
yes.
So it just takes the strong.
I'm sorry?
Voltage. of the two?
I'm sorry, say that again. My internet's kind of
It just
unstable.
takes the stronger voltage of the two? Oh,
Yeah, yeah. If either one is high, if either one's 5 volts, then the voltage drop will be like around
okay.
a little bit less than 5 volts.
So it basically takes the higher voltage of the two, and that's the voltage drop in the circuit.
Yeah, it
Is
takes
that
the
what you're
higher of the
saying,
two.
okay.
Well, and if they're both high, then this will be a high voltage too.
Okay.
Okay. And then you can actually, okay, well, I'll show the other one. This particular circuit, the voltage here is high only if the inputs are both high. Because if these are both zeros, then the current will go this way. And the voltage drop across here will be 0. This is called an AND gate. Another digital logic circuit. So diodes can be used for digital logic. Okay, amongst other things, you can shape voltages. You can take an AC. You can take an AC signal and convert it into DC. Those are called rectifiers. Yeah. So they have a lot of applications. Now, I want to focus on this equation because when you collect the data, you got to do a curve fit to this equation. So you're going to need to make this a fitting parameter. And you need to make this a fitting parameter. The less fitting parameters you have for this one, the better. If you want to add a fitting parameter, I would just put an additive constant. The most you need to have is 3. But the thing is, you have to define your own curve fit. So those of you who have graphical analysis, and unfortunately I can't show graphical analysis on my computer because it doesn't work on my computer. If you're using graphical analysis, you got to use the define curve fit function. So in graphical analysis, in that piece of software, you have to click the button that says define fit, which means that you have to type in an equation your V is your X, I guess, your X component. This is a number, that's this number. And if you want to put a C here, you can, but you don't need that. You don't need that one. So you have to type in your own equation like this in order for you to do the curve fit. Same thing if you're using Cy Davis to do the curve fit. Those of you who use Cy Davis, you have to actually define your own curve fit. So if you're using Cy Davis, can I have Cy Davis open?
Where did that -1 come from?
That's part of the curve fit. I mean, that's part of the equation.
Is that inside or outside the E?
Oh, yeah, you're right.
Okay, good.
Sorry, it's outside. It's like this. I'm trying to type it like you would on a computer. So let me open. So if I were in Cy Davis, oops. and I was doing a curve fit, I would go to Fit Wizard, and I would go to user defined, and let me call this user 5, whatever you want to call it, doesn't matter. And I use parameters A and B, and I'm going to type A star EXP of X over I gotta be careful now. The hard part is making sure you typed it in correctly. Formatting's. In fact, I gotta be careful here. I gotta do this. That B that I have there, oops, you can't see that very well, can you? I can't change the font, unfortunately. That is so small, I apologize. I'm sorry you can't see that very well. But when you type that in there, you just type the equation like you know, I'll copy and paste it into Word so you can see it. What I did is I typed in the equation, it looks like this. Okay, and I determine my fitting parameters. By the way, that B, I can always put that B in the numerator, and then I take the reciprocal of it, and that'll give me my N value. So my B is my N value. You can call it N if you want, I don't care. Okay, whatever you want to call it. So when you do your curve fit, then you can just save the name, and then you can click on the button fit with selected function and then fit it. Okay, I'm not going to do that here because it's probably going to act weird because I have a linear function. Is that okay? And those of you who are using graphical analysis, you got to do a user-defined function because you don't have that function built in. I don't even think. Yeah, see, the built-in one in SciMath is not what we want. So you do have to define your own fit. Are we okay with that? Okay, I just want to make sure we're okay. So by the way, I did grade the labs. Actually, I graded both for you guys. I graded both the multimeter quiz and the properties of charge. The videos were nice. For some things that I took off points or for things that weren't done. That's all. But overall, they were nice. So I grade, the actually written lab report a little bit more picky, so be careful with sig figs. Okay, be careful with sig figs, especially when you're calculating percent error. I tend to be, what I look for is things you forgot about or mistakes you made when I grade the lab. That's really the written lab. So make sure you're careful and pay attention to details. Because part of doing experimental physics, or just, it doesn't have to be physics, but part of doing an experiment is actually paying attention to the details. Okay? Evaluating your data, making sure your data is valid, making sure you've assessed the errors in your experiment properly, etc. Okay? So just be careful with that. I think I showed you last week. If I go to our course, I don't have it there, darn. Under the modules, I have lab report reminders. If you click on it, it shows you my pet peeves, basically. Those are my pet peeves in lab reports. Never use the term human error. Okay, remember, human error just means human error is very vague, so don't use that term. So I want you to make sure you go through these general reminders. Those are my pet peeves in writing lab reports.
This lab, do we worry about the conclusion error or stuff or not?
No, not for this lab. I'm thinking which lab in this semester is going to be where you have to worry about the conclusion. I can't remember. I don't think there is one. When I teach 215 or 205, I spend more time on doing the conclusions, and especially the way this semester is going. The way this semester is set up, there really isn't a lab like that. Like the sample I gave you was a lab where a student measured a physical constant, and they were supposed to see if it agreed with the expected value, with the accepted value. So there you can write a nice formal conclusion. This lab is more like learning how to wire things and understanding how some components work. That's about it. And even the next lab too is more on wiring and understanding the Kirchhoff's laws and series and parallel, but not really looking at verifying something directly. So I don't have any lab this semester where I actually really have you write a formal conclusion. But you'll have more practice at it in 215. So, other questions? Wait, so one of the things, when you write numbers in scientific notation, use the superscript feature in Word. Don't just put carets, like you see there. Let me blow this up. I don't know if you can see that. Don't use any of these formats. E means 2.71a, right? I know this is acceptable in, this stuff is acceptable in WebAssign. That's because WebAssign only does superscripts when you write a symbolic answer. Okay, but Microsoft Word can do superscript and subscript, so use them. Use that feature. Okay. So what is the rule for sig figs on percent error and percent difference? Just as a review.
Isn't it only 2, right?
Well, let's go over that then. Let's go over that real quick. Suppose I make a measurement. And I'm going to follow the rules for sig figs strictly here. And remember, the rules for the sig figs are just rules. What we use are the theory of errors, the ones what you get from error propagation. That's what a scientist really uses. But let's say I measured pi, and I got 3.143. Okay, so this is the measured value, the accepted value. Is that. So I want the percent error, which is the difference between the two. Now, what are the rules for subtraction?
You take the least accurate.
Least precise, you mean?
Or yeah, at least you round to the least precise, and then that's the amount of sig figs.
So what about this one? What do I round it up to?
Well, you'd round it to 0.002, right?
Right, because 5, I round to the nearest even. That's our rule. I round this to the nearest even. How many sig figs is that?
That's 1.
1. So I'm going to take this number, and really, I should, so this is 1 sig fig divided by, I'm sorry. 1 sig fig in the numerator, and then I'm going to divide by whatever that is, n times 100. I have 1 sig fig in the numerator and a bunch in the denominator. How many sig figs are going to be my percent error?
Just 1.
Just 1. So this will have 1 sig fig, but now be careful. The general rule of thumb is don't round off here. You round off at the end. You keep 1 extra digit and then round off at the end to 1 sig fig. That make sense? You don't round it off in the numerator because you're going to lose some accuracy. You actually always, the general rule of thumb is to keep 1 extra digit when you do multiple calculations. Does that make sense?
Yeah.
Okay, so 1 sig fig at the end. If the error was bigger, then this might be 2 sig figs. The number of significant figures I'm going to have in my percent error calculation is going to tell me how good my result is. If I have 2, that means I have a bigger error. Does that make sense? And then, if I do the following, because these are things that students make mistakes on. Let's say I measure 4 quantities. What's the average? Well, I'm going to sum them up, right? So I take 10.00, divide by 4. How many sig figs in my final answer? Taking the average of four measurements. If I average these 4 numbers, well, how many sig figs am I average?
4.
Right, according to the rules for sig figs, I should do this. Right? Now, how do I really know I should keep this many? This is where the rules for sig figs really don't work. What should I do is calculate the standard deviation and then the standard error or the uncertainty. When you calculate the uncertainty, that's going to tell you how many decimal places to keep and how many sig figs to keep. This is what tells you how many decimal places to keep. Okay, not really the rules for sig figs, because the rules for sig figs are just set of rules that don't always work. You folks know how to calculate a standard deviation and a standard error or uncertainty. So you would, in your case, calculate this and then keep the number of sig figs based on this, what this is. Okay? Whatever that comes out to be. Because if the standard error came to 3 decimal places, then I'd be okay with this. But if the standard error or the uncertainty came out to 1 decimal place, then I would write 2.5 plus or minus. Okay? So this determines, in reality, how many decimal places or how many sig figs to keep. The rules for sig figs are not the best way to do it. You do it in high school or maybe in a class where you haven't been taught this. Okay, but you guys have been taught this. So this is where the rules for sig figs are ambiguous. So you use this. In fact, you'll have some professors say you can only keep this many decimal places because none of these measurements are to the third decimal place. One can go either way on that because the rules for sig figs are ambiguous in this case, unless you know the uncertainty. Okay. Any other questions? You have questions on the homework? Let me go to WebAssign.
I do.
Okay.
I guess I actually have two. For number 11, and also then number 15. Well, kind of number 15.
All right, let me open it up. Okay. So what is your question? Number 11. Oh, sorry. Let me see if I can blow this up.
It's just kind of confusing because there's like, it seems like there would be, oh, actually, okay, I think I get it. Because I was originally saying it would be 0, but that would mean that there's a potential drop across that resistor, and there isn't because it follows the path of least resistance.
So, it wants to know the voltage, right? It doesn't want to know the potential difference.
Yeah. Well, yeah, because on the bottom side it's 12, right? Because that's the negative end of the battery.
Yeah.
But then I was thinking it'd be 0 because there's no current there, or yeah. But I guess it has to be, well, flowing through that resistor.
Yeah.
But then that actually means that the voltage would still be negative 12, which I guess I kind of answered my own question.
Okay. All right. So what was your other question?
Well, number 15, I mean, I assume did you make a video on this? It's like the theory one, basically.
No, I haven't.
Okay. Because you just, I don't remember, what integral do you use for this is what I'm kind of trying to figure out.
So, the resistance R is rho L over A. Okay, so...
We can't see the board.
Oh,
Yeah, we can't see the board.
sorry.
It's fine.
Thank you. Okay, so your resistance is RL over A. Sorry about that. So we got to write an expression for dr. Let me take a look at the problem here.
You have to find like the potential difference between the two plates, basically.
No, you don't need to. So what happens is the current goes from the inner radius to the outer radius, right?
Yeah.
So the current is going this way. So you want to look at the resistance from here to here, right?
Oh, so the resistance is Okay, I get it.
It's
What
traveling
kind
in this
of-
direction. So you got to.
It acts. So there's like a theoretical like wire, right? I guess you could make it the water.
I'm sorry.
Oh, I was saying that. So the water kind of acts as like a theoretical wire between the two plates.
Well, it's your resistance, right? The water
Yeah.
acts like a resistor between it from here to here. You okay with that, or?
Yeah, yeah.
Okay, so you need to write an expression for dr, and I might make a video on this, but write an expression for dr in terms of, how would you write it though? How would you write it?
Well, the length is infinite. So
Yeah,
when you use like
but it's traveling this way, right?
yeah.
The area is going to be, what is the area going to be? Isn't it going to be the area of each surface that makes up this, the lateral surface?
Would it be like A1 minus A2, like the outer minus the inner?
I mean, the area is
Because
going to be,
Yeah.
the amount of current going through each one of those areas. Isn't that true? And then you draw a thickness. Just imagine. Let me use a different color. This is going to be so hard to draw, sorry. The current is going through this way, but this is a cylinder that comes all the way out of the plane of the screen.
Is
can
A
make
the
this-
cross-sectional area?
dr. So it's going through a dr, but the area is this. And I better be careful with my letters. Right? Isn't it true that the current's going through a bunch of cylinders, hollow cylinders of thickness dr?
Yeah. Okay, so the area of each cylinder is 2. Okay, that makes sense. And you're integrating from R sub A to R sub B, right?
Yes.
Okay, that makes a bit more sense.
The integral's easy, right? Now that I had this set up. So you got
Yeah,
to be
and
able
that's yeah.
you got to be able to picture how the current's going through this thing. It's going this way, right? You're looking at the potential difference between these 2 points and the current from here to here. And so the current's going through, you got to think of it, the current's going through a bunch of cylinders of thickness dr. And surface area 2 pi RL. Yeah, there is one similar in the book. Okay, and then once you've done that, the integral's easy. The hard part is setting it up. The math is actually pretty straightforward in this one. Are we okay with that? Because it's pretty obvious now what the answer is going to be, right?
Yeah, it's like rho over 2 pi L times ln RB over RA, right?
Yeah, that's
Something
it.
like that. Yeah. Okay, that makes a lot more sense. Yeah, getting the DR was kind of like I wasn't sure what I was supposed to integrate, but I just knew I just had to integrate something.
Yeah, you have to
That
break
makes sense.
when in these kind of cases you have to break it up into a DR and then add all the DRs up. Think about which way is the current
okay.
flowing. I mean, even if you have a rectangular conductor, although the math is easier, you want the resistance. If you hook up a power supply between these 2 points, or between these 2 points, or the top and the bottom, the resistance is going to be different. Because the area is going to be different, right? If I hook a power supply between these two ends, the area is going to be different, right? The cross-sectional area is going to be different this way as opposed to if I applied between the top and the bottom. That area is going to change. So will the length. So you got to consider how the current's going to be going through your system. And that one's probably the hard problem, the hard problem in the homework.
So we just like considered small cylinders and then added them up together. Like we took the integral of the small cylinders.
Yeah. So each cylinder, you imagine this is made up of, well, not tree rings, but then a bunch of cylinders coming out of the board and you're just unwrapping them. I wish I had a prop. I don't have a prop for that. I could do this, I guess. So this is one of the cylinders. Okay? And so the current's going through this whole area. Right? The current's going through this whole area. The electrons are going this way. And so all I do is find the resistance of each one of the cylinders. I make these cylinders bigger and bigger and bigger and add them all together. So this is one of the cylinders. That make sense?
Yeah.
Okay. Yeah. Also, did we miss an L in the denominator?
Yes.
Okay.
Sorry. They'll cancel, I guess, so. No, there is no L. No, that's not. I'm sorry. There is no L. This is your L.
Yeah, the L's the DR. Right?
Yeah. That is your L. Sorry.
I think that was the most confusing part. There's so many R's and L's.
Yeah. Yeah, because there's an R here for resistance and an R here for. It's easy to get confused. I got confused right away with the L's. Other questions?
Man, now I feel smart.
That's good.
But I won't feel smart on the test.
This one shouldn't be as difficult as the first one. Oh, by the way, I still got to write the key for you guys. So I'm not write it, but make a video of the key for you guys. So I apologize.
Well, we get one drop test right, so.
Yeah. But make sure you take the last one. The last one doesn't count. The last one you have to take. The exam 5, because it only counts as 9%. Other questions? I think the rest of them are not that bad. Isn't that true? The rest of the homework problems for this assignment aren't that bad because there's a lot of multiple choice questions. Like 12, 13. 14.
Yeah, this one's pretty easy.
Okay, that's good. That's why I give you guys a little bit less time and more time in the last one. The last one in this unit, there's a lot more blanks to fill in. That's because you analyze a circuit, you can figure out all kind of stuff from the circuit. So they're not long problems, a lot of them, but they're just a lot of information you can get out of them.
Did you do 5 part D? I got everything else. I got easily, but part D, I'm missing something.
Part D, you have to use the resistance on the resistor as a Q or V, or no, something like that.
Okay, so we have let's see. The charge is placed on a capacitor, and then the capacitor is placed into the circuit as shown. And the resistor is initially, where is it? The 3C is initially uncharged. So you're able to do parts A, B, and C.
Yeah, I got those.
Okay. So the internal energy in the resistor is whatever is lost by the system.
Oh, so I'm just subtracting.
Yeah. So whatever you, yeah, it's basically the total initial energy. I'm sorry. Let me. Yeah. If I want to write it as a positive number, the total initial energy minus the total final energy. You can use q squared over 2c. I mean, however you want to do it. Yeah, so it's just a difference. So when I did the capacitor problem, the charge sharing problem in the capacitor, and I said, what's the change in energy? That's really the energy that's lost. So I would do it in terms of q squared over 2c. Well, Andrew, one of them is 3 over 32nd. The other one's not. For part C. I'll say that.
Yeah, and then just so the sum of those subtracted from the initial.
Yes.
Okay, that makes sense.
Okay. Are there questions? Yeah, one's 1 over 2, the other one's, how much is the other one? Over 8. That's correct. Yeah, q squared over 2c minus q squared over 8c. That should be the answer. Because that's the energy that's lost. And that goes through the resistor. And that appears as heat, thermal energy. The resistor gets warm. Although you probably won't feel it.
Actually, I do kind of have a question on that. Like thinking about it theoretically,
Yeah.
when you're finding the initial energy, where does the C come from? Because like there's no capacitance on the resistor. Or are we just thinking about the capacitors and then the resistor takes what's left?
Yeah, the resistor takes whatever's lost by the capacitor.
Okay, so we're calculating basically the initial state of the capacitor and the final state of the capacitor.
Yeah, yeah,
Okay.
you don't have to have an R in there. Right, you don't need, yeah, you don't have to have, it's just written in terms of those values.
All right, cool.
Professor,
Yeah.
for question 10 or 11, I was just wondering what happens at point A.
At point A, let me take a look. Let me blow that up, sorry. Isn't point A at ground?
Yeah, like when the current gets there, what happens? Does it just go straight to ground?
Yeah, if you ground it.
Oh, okay. Well, yeah, that was simple. Sorry, thank you.
Sure. Other questions? So we're okay with the rest of this then?
I'm all good.
Okay. So I don't have anything, unless you folks have questions, I don't have anything new. So you have the Ohm's Law lab, and then the next lab will be DC circuits. So that one's going to be a more substantial lab and lab report. That's going to be a pretty substantial one. And then the lab after it is a project. So I'm going to assign it, and then you're going to work on it, and you'll have until like November 25th to complete it. So that's the one where you build a motor. And you have to pace yourself. I mean, the motor lab, you don't want to do it the last minute. Please don't do that at the last minute. In fact, any of these labs, don't do them at the last minute, because if there's a problem, I need the motor lab we know works though, because we've done it for many semesters. But the Ohm's Law lab and the subsequent lab, I need to see what kind of issues you're having. So like, for example, the properties of charge lab, I noticed that, the glass didn't work very well. So next semester when I do the lab, I'm probably not going to have students use glass, because if I'm not with the student, it's very hard to make it work. Okay, so whatever issues you have, first of all, I need to know. And then second of all, try to do the lab early, so we can try to, if you have problems, we can try to fix them. Okay?
I have another question, actually.
Sure.
For number 3 on the homework, so when you're calculating resistance using rho L over A, the A is the cross-sectional area, right?
Yeah, well, you got to remember, you got to think of which direction the current's going through, right? So if it's going through along the long end, then the cross-sectional area is a square
All right.
that goes into.
And you're integrating basically on the length. Is that?
Well, I mean, this one we're not integrating, but
Well, so how would you calculate that?
it would be rho L over A. But let me see
You
how
just
it's.
consider them in series, right?
Yeah, they're in series, so you can do each one of them separately.
Oh, so you just plug in like what at 25 centimeters for L and whatever
For one.
you would be 4 millimeters squared for A, or 4 millimeter.
Yeah, you got to convert that to meters, but
Okay, yeah, and
Yeah,
then
yeah.
you just do it in series. Oh, okay.
yeah, because
Because I was assuming, yeah.
you're sending current along the long end, right?
Yeah.
Because if you had it across, if you're running it from the top to the bottom, then your cross-sectional area would be much bigger.
Yeah. Okay.
Yeah.
All right. That was my only question.
Okay. All right, so if you folks don't have any other questions, I'm done then. Are we okay? All right, you're welcome. I don't want to
Yeah.
end
Thanks.
it.
It was nice. Helpful.
Okay. All right, you're welcome. I will end it here. We'll see you next time.
See ya.